My name is Soshu Kirihara, come from the Osaka University, Japan. And today I would like to talk about directional fabrication of the ceramic components by using ultraviolet laser lithography of additive manufacturing process. So at first I would like to talk about the stereolithography and the conventional type and the three-dimensional fabrication process. In our investigation groups, we try to fabricate the various kinds of three-dimensional structures. For example, the periodic structures and the self-similar fractal structures by using ceramics or the metals and the composite materials. So the plate-shaped structures and the three-dimensional structures were fabricated by using stereolithographies. So this figure shows the principle of the photonic crystals. Today I would like to talk about the periodic structure fabrications of the photonic crystals. So here is the dielectric materials. So the periodic structures possible to reflect the electromagnetic wave whose wavelength is similar to the periodicity like this by Bragg diffractions. So in this case, the photonic bandgap and prohibited and bandgap areas created in the frequency range in the transmissions attenuations. In this case, and the standing wave A and the standing wave B form in the crystal structures, and the standing wave A vibrating in the air region with higher frequency, and the standing wave B vibrating a material region with a lower frequency. And between higher frequency and the lower frequency, all electromagnetic waves will be reflected by Bragg diffractions. So that in this area, the photonic bandgap areas, electromagnetic wave impossible to transmit to the opposite side, and this means a perfect reflections of the electromagnetic wave. If you create cavity-shaped photonic crystals, you can transmit the electromagnetic wave for one directions, and you can create like the plate-shaped crystals that it realizes the barrier functions of the electromagnetic wave. Of course, the parabolic shake and the photonic crystals realize the direction transmissions of the microwave, millimeter wave, or the more higher frequency electromagnetic wave. What is the ideal structures of the photonic crystals? The one type is like this, the diamond type, because here the diamond type photonic crystals possible to open the photonic bandgap for all crystal direction like this. So this blue band shows the common regions for the all directions photonic bandgap. So in this frequency areas, electromagnetic wave impossible to transmit to the any directions of the artificial crystal directions. However, and of course this photonic crystal is a perfect structures. However, and it is difficult to fabricate like this complicated lattice structures by using a conventional fabrication method. So in our investigation group, we try to fabricate the photonic crystals by using a stereolithography like this. Here this figure shows schematic illustrations of the photonic crystal fabrications. Here is a photosensitive resin. This resin solidifies the UV laser irradiation. So the laser scanning, and we can create like this the line shape and solid materials. And these line structures was created, many lines were created on the like this stage plate. And layer by layer stacking process, we can create the three-dimensional structures. So we can create the plastic three-dimensional structures by using only the laser scanning and the layer by layer stacking. This figure shows the created and the photonic crystals. In this case, the epoxy mold and inverse the lattice structure, inverse diamond structures was created by stereolithography. And the barium titanate and the paste materials insert into the three-dimensional mold, so we can create a photonic crystal like this. However, it's difficult to inject to the material paste to the three-dimensional mold, so we try to mix the ceramic particles into the photosensitive liquid resins. In this case, two-dimensional structures by using a laser scanning, and through the layer by layer stacking, we can create a three-dimensional pattern like this. So we can create by only the laser scanning and the layer by layer stacking, and we can create a complicated shape 3-dimensional structures by using a stereolithography process. Okay, this figure shows the fabricated diamond photonic crystals. In this case, the titanium dioxide particle was dispersed into the epoxy matrix, and the volume fractions just only the 10%. So the direct constant is not so high. However, these 3-dimensional structures and the periodic structure directions is about 10 millimeters. So the possible to reflect the microwave by using these 3-dimensional patterns. Okay, and the microwave property was measured by using like this the metal tubes. Okay, and here is the antennas, and here is antennas, and the microwave transmits the samples, and and the transmission attenuation measured like this. Okay, if the fabricated photonic crystals possible to reflect electromagnetic wave in the limited frequency range, attenuation will be decreased like this. The U-shape profile will be obtained. Okay, and this figure shows a fabricated titanium dioxide particle dispersed epoxy diamond photonic crystals. You can see the 111 and the 100, 110 crystal plane obtained according to their computer graphic data. Okay, so the microwave transmits to the 111, 100, and 110 directions. Okay, this figure shows a transmission attenuation of the microwave. You can see and all crystal directions, and from 12 gigahertz to the 70 gigahertz, and the band gap form of all crystal directions. For example, the 15 gigahertz microwave impossible to transmit for any directions. This means the perfect reflections. Okay, so the next, and the electromagnetic property of the photonic crystals possible to calculate by using the solving Maxwell equations. In this case, a plane wave propagate into the photonic crystals for all crystal directions. The most important thing, most difficult thing is how to enter the 3-dimensional structure to the Maxwell equations. However, in this case, a computer graphic data were cut for the 32, 32, 32, and the XYZ data, and the digital data were entered into the Maxwell equation automatically. So, okay, this figure shows the obtained electromagnetic band structures. This yellow line shows the Maxwell equations answer. Okay, here there are many Maxwell equation answer, and then of course this lower frequency and also. So there in these areas the Maxwell equation have answers. So the electromagnetic wave possible to transmit to the opposite side. However, you can see that these regions, there are no yellow lines, so the electromagnetic wave is impossible to transmit to their opposite side. So this means perfect photonic band gap formation reasons. So the solid circle shows a higher edge and the lower edge of the measured photonic band gap. You can see the calculated result and the measurement result has good agreement. Okay. Anyway, we want to try to control the higher frequency electromagnetic wave, especially called the terahertz wave, the micrometer order wavelength electromagnetic wave. Okay, this far infrared ray regions and possible to detect like this small weapon behind the newspapers, and it's possible to detect dangerous rock and by using a transmission viewing system. Anyway, we have to fabricate a micrometer order diamond type photonic crystals to control the micrometer order wavelengths and higher frequency terahertz wave. Okay, this figure shows a fabricated and micrometer order photonic crystals by using a conventional stereolithography process. And you can see the micrometer order lattice obtained. However, in this case, we used only the 0.1 millimeter 100 micrometer spot size laser beam, so it is difficult to create like this micrometer order structures. And the most important thing, these are composite materials. The epoxy matrix absorbs the terahertz wave, so we have to create a more clear micrometer order diamond type 3-dimensional structures, and by using a perfect 100% ceramics lattice. Okay, the next process is a nanoparticle pasting process. Okay, we tried to increase the ceramics particle dispersion amount in the photosensitive resins. And in this case, the 40 volume percent alumina particles, and in this case, the particle diameter is 170 nanometer, were dispersed into the acrylic, photosensitive acrylic resins, okay, by using a rotation and a revolution mixing machine. In this case, rotation means mixing like this, and the revolution means like this, the mixing. The revolution is the degassing, and the rotation is the mixing of the particles and the solid particles in the liquid phase. Okay, this is a movie that you can see there. Okay, at first the paste material is very hard, higher viscosity. However, if you introduce the stick and turn around the paste, and okay, you can see the paste material shows smoothly fluid flows. Anyway, we can control the viscosity by introductions of the shear stress. So this high viscosity paste was spread on the glass substrate by using a mechanical knife edge, and in this case, a layer thickness and 30 microns. Okay, so the laser beam scanned on the paste surface, so we can create a solid two-dimensional structures. And spread and the laser scanning and the layer by layer stacking process, we can create three-dimensional structures in unsolidified paste materials. After the fabrications, the three-dimensional structures are put out and washing and drying, and we can obtain the composite materials. Okay, so this movie is stereolithography fabrication. Okay, paste materials and spread on the glass substrate. Okay, and this white color is laser scanning. Okay, so the paste materials are spread on the they are on over. Okay. Okay, this figure shows a fabricated micrometer order photonic crystals. In this case, the alumina particle are dispersed into the acrylic resin matrix, and the volume fraction is 40%. Okay, okay, you can see the micrometer order. The diamond lattice was obtained by using a laser scanning stereolithography process. So, of course, these are the composite materials. We have to create a full ceramics micrometer order. Okay, by using a conventional dewaxing and sintering process, we can create the full ceramics three-dimensional structures. Okay, and after higher temperature sintering process, we can create the full ceramics diamond lattice. Okay? You can see the diamond planes in 111, the 100, 110. Okay, and you can see the micrometer or the alumina lattice and the translucent lattices. And reached the relative density. In this case, the 99.8% with higher density. Okay, so we can create the full ceramics diamond structures by using a stereolithography and heat treatment process. And the terahertz wave property was measured by using like this optical system. At first, a femtosecond laser beam inserted into the micrometer or the antennas and generated the terahertz wave transmit sample and detected the same shape micro antennas, and we can obtain the intensity and the time and the pulse data, so that by using Fourier transformations, and we can obtain the transmission spectrum. Okay, this figure shows obtained transmission attenuations, transmission spectrums. Okay, and you can see there 110, 100, 110 directions, and we can obtain the photonic band gap in the similar frequency range. This blue band shows the common regions of the all crystal directions. For example, the 0.4 terahertz wave impossible to transmit any directions. This means the perfect photonic band gap formation. Okay, the photonic crystals, why we call these structures the photonic crystals? Okay, here is a schematic illustrations of the semiconductors. These materials compose of the periodic structures of atoms. These periodic structures possible to reflect the electronic wave by Bragg diffractions. So in this case, the electron band gap form in the energy band. And if you introduce the donor or the acceptors, the structural defect to the semiconductor, you can create a localized mode in the electronic band gap, and you can control the electronic wave transmissions by introduction of the structural defects. And of course, in the photonic crystals, imitation of the semiconductors and this periodic structure, direct material periodic structures possible to reflect the electromagnetic wave by Bragg diffractions, and the photonic band gap open in the electromagnetic wave transmission spectrums. And if you introduce a structural defect, you can control the electromagnetic wave transmission and create a localized mode in the band gap. Okay, so similar logic, the photonic crystals and the semiconductor natural crystals. Okay, this figure shows introduce a point defect in the perfect photonic band gap. Okay, so of course this hole was fabricated under stereolithographic additive manufacturing process. Okay, this figure shows a calculated result. In this case, the incident wave and the localize and resonate here, and all here is the perfect reflection structures, and making a standing wave increase the powers and transmit to the opposite side. In this case, half wavelength localize here, and in this case, one wavelength localize these directions. And these electromagnetic wave only transmit for opposite side. Okay, this figure shows a the measurement result. The photonic band gap opens by your perfect photonic crystal structures, and the introduced the structure defect creates a transmission mode of the transmission peak of the localized modes, okay, in the specific frequencies. Okay. This figure shows the created ceramic crowns. Okay, we can create various kind of three-dimensional structures in the photonic crystals, of course, the photonic crystals and the bioceramic structures, and we can create various kind of materials and three-dimensional structures. However, we have to create the three-dimensional shape by stereolithography, and if you obtain the full ceramic structures, we have to use the heat treatment process. Anyway, we need two processes, shaping and heat treatment. So the next trial, direct ceramics fabrication by using a laser scanning process. Okay, in this case, laser beam, out-of-bite laser beam powers increase to the 1 watt. This is 10 times higher comparing with the conventional stereolithography process. Okay, so increase the power out-of-bite laser beam, realize the waxing and through the resin decompositions and sintering by using electromagnetic wave resonation, localizations, and absorption. Here is the ceramic base materials. After the waxing and sintering process, remaining ceramic particle was sintered and creates the plate-shaped structures on the substrate. Okay, this figure shows a laser drawing process, and the bright color obtained the laser spot side. And after laser scanning, we can create like this plate-shaped materials. Okay, here is microstructures. You can see the micrometer or the bulks created in the microstructures about 5 micron to the 8 microns. And of course, at first, the ceramic particle size is under the 1 micrometers. So the micrometer or the bulks were created by laser beam irradiation. The most important is plate face thickness at first 15 micrometers. However, after laser drawing, the layer thickness decreased to the 25 microns. This means the ceramic particles dispersion is 50 volume percent. So the waxing and sintering shrinkage occurred to the only z directions. So it is possible to realize the layer by layer stacking process. Anyway, in our investigations, and we used ultraviolet laser beam and 355 nanometer wavelengths. Okay, in this case, the half wavelength easy to propagate between the particles and the penetrate into the inside of the paste materials and increase the temperatures. So the resonation and the localization occurred over the inside, so that the resin dewaxing and the powder sintering were realized the inside of the paste materials. However, if you use the infrared ray and wavelengths in the very longer, and the laser beam impossible to penetrate into the paste materials, so they're okay by laser beam scattering. Anyway, layer by layer stacking process, we can create micrometer or the 3D structures. In this case, a titanium photonic crystals was created by ultraviolet laser scanning process. And at first, here is a micrometer or the structures. However, in this case, the nanoparticle were coagulated into the 3D structures. So the scanning speed increased to the twice. 2 times, and the scanning speed 100 micrometer per second, so we can obtain the more clear micrometer or the structures. However, you can see the black area remained. Of course, this is the remained carbon elements, so the irradiation power was increased to the 600 milliwatt to the 700 milliwatt, so we can obtain the white colors micrometer or the titanium dioxide lattice was obtained. In this case, the relative density is 97%. Okay, high density, however, not so. We want to try to the heat treatment. So, in this case, after heat treatment and the lattice crystal structures was lutile structures or higher dielectric constant. Okay, and by using directional fabrications and ultraviolet laser lithography process, we can create the twin diamond structures. Okay, here is real structures, and these dotted lines are twin defect. Okay, here right side and the left side has a mirror symmetric diamond lattice. Here is a plane defect. This area is possible to localize and resonate electromagnetic wave. In this case, the sintering density reached 99.5%. Okay, this is localized simulations, and the wavelengths and the electromagnetic wave localize and resonate here, and reflects my perfect mirror structures and increase the powers and to transmit to the opposite side. Okay, this figure shows the calculated results and measurement results. Here is a band gap, and here is a localized mode formed by introductions of the plane defect of in the twin diamond crystals. Very clear photonic band gap and localized mode was obtained in the measurement results and the calculated results. Okay, in this investigation, we try to fabricate the 3D structures by using additive manufacturing process. At first, the 3D diamond structure was designed, and the 3D pattern was fabricated by a stereolithographic additive manufacturing. And the electromagnetic wave property was measured by a computer system and obtained the result feedback to the 3D designing. By using like this investigation circles, we can create the ideal structures, and by using computer-aided design, manufacturing, and evaluation process. Anyway, this is last slide. In our investigation groups, we can fabricate various kinds of three-dimensional structures. Of course, the ceramic structures and the metal structures and the composite materials. And today, I talked about the periodic structure fabrications and the electromagnetic wave controls by using photonic crystals. Thank you very much.